And we're welcome to the Winds and Currents webinar. And we're fortunate today to have Stoffelen, who's going to talk about harmony. So this is the European counterpart to what a Odyssey proposal would represent, but a really different sort of mission. And I'll let you take it away, Ad.
Yeah, thank you, Sarah. I'm pleased to provide this talk on behalf of the Harmony team. I also say something about SeaStar. So these all fall into the ESA Earth Explorer missions. I show a full list here, so you can imagine that ESA Earth Explorers also cover many aspects of the Earth. On the bottom you see Harmony, Earth Explorer 10, and you also see a date or a year, 2030. That's more or less the projected launch time of this mission. You also see that Earth Explorer 10 has only one name to it, which is also quite important because it's actually the only mission considered in the Earth Explorer 10 program. The ESA Earth Explorer program is, of course, paid for by its member states, and there will be a so-called ministerial ESA conference this autumn, where this whole Earth observation program, of which the Earth Explorers are part, will be discussed and we expect also approved. SeaStar, in fact, is part of Earth Explorer 11 missions, and there in that in Earth Explorer 11 we still have 4 candidates, and SeaStar is one of them. So you could say a 25% chance of that mission being approved. So it is about processes at the air-sea interface, and I know that many of you listening are concerned with those, and this is a quite a complex depiction of all these different processes. And you see that here we both show processes at the in the ocean, the top of the ocean, and in the atmosphere. Also show some boundary layer rolls and some clouds, and it's also all about air-sea fluxes depending on surface stress, boundary layer processes, and small scales, so kilometer scales. The idea is that the atmosphere and the ocean are dynamically coupled through parameterizations, and that these parameterizations have errors. Nevertheless, 70% of the Earth's surface is ocean, as you know. And therefore have the specification of these parameterizations and the fluxes, they actually have a big impact on the dynamical system. So also on the larger scale modes, so these small scale processes feed larger scale modes. If you get the small scale processes wrong, you also may get errors in these large scale modes. So, for instance, tropical modes are poorly described, like the El Nino, Medellin oscillation, or tropical instability waves. And of course, the main question is, will these modes change in the changing climate, and with what consequence? Like we should say, this summer in Europe, we are particularly concerned about changing modes in the weather. And that's not only in Europe, but I think also in China, and probably also in the US, there are some dramatic differences of these summers with previous summers, and it of course has to do also with the fact that the flow is not the same as it was before. And the question is that a consequence of climate change, or is that just part of the weather? So these are quite relevant questions, and modeling the Earth system is dynamically is also very important. So a warm world implies more water vapor in the atmosphere, more evaporation, more cloud, liquid water and ice in the atmosphere, and more rain. That also probably includes more enhanced cloud dynamics, maybe more cloud organization, more updrafts and downdrafts, wind. And then we go to the associated dynamical mode changes. So will we see less cloud or more marine aerosol? So that you can pose many questions that have to do with the changing climate. And these are just a few of them. We already know that there is issues with models. We just are launching a level 4 product in the Copernicus Marine Service based on spectrometer data. And we've been looking at mean differences between spectrometer winds and ECMF model winds for a long time. And at the top, you see a typical annual mean meridional wind speed difference of spectrometer winds and ECF winds in era 5. And if you look at the scale on the right-hand side, you see that the differences in the tropics in particular are very substantial. Actually, they're like 20% of the mean wind, so that's quite big. If you look at variability errors, that's the lower plot. That's showing the transient wind speed difference between spectrometer, METOP AASCAT, and collocated ECMF era 5 in 2018. And also there you see in terms of variability, there's a big difference between spectrometer and model. And also on the right hand side, you can read that on the scale. Also, you see that the color is only red, which means that actually it's lacking variability in the model, which of course has also consequences for fluxes. We also with spectrometers have been able to look at moist convection. You see some graphs here where we show that about 30 minutes after extreme convergence, we see heavy rain appearing in Meteosat rain products. The same thing before extreme divergence, there was heavy rain 30 minutes earlier. So all these convergence and divergence that we see, these extreme divergence and convergence we see in spectrometers seem to be therefore well related to other products of rain, which is very consistent with our idea of moist convection. And then, of course, we all can compare the ASCAT convergence and divergence with the ECMF convergence and divergence. And again, here we see that these extreme convergences and divergences that are associated to rain actually do not appear in the ECMF model, which have a much smaller range of divergence. Of course, this lack of variability must have some implications on the fluxes and the global dynamics, which we should further investigate. This is an animation from a run we did with a cloud resolving model, where we couple also to the surface. Just showing this. So you first bit, you see actually the surface roughness changing, then you see the clouds from the top, and now you see the clouds from the side. And you can actually see the association. You see also the rain here at the bottom coming out of the clouds. You see that these patches are associated on the surface. The roughness patches are associated with the cloud patches. So there's clearly a link between the clouds and the rain. I just play this again because I think it's a quite nice animation. This animation is not very long. It takes only several minutes, but you also see that in this time scale, also the clouds are moderated quite a lot. So also the entrainment of the clouds is visible in this cloud resolving model. So these animations look quite realistic, but of course the main question is how real is this? Because everything you see here is either resolved in the dynamical equations of the model or still parameterized in the model. So this is again a model, and these models are used to further develop parameterizations for larger scale models. And the question that we would like to answer with Harmony is how good are these models? So what we did in the preparation of Harmony is to run this cloud resolving model, use our sensors that we will have in the Harmony mission to measure clouds, to measure the surface, and then do retrievals, and then bring those retrievals back to the model truth, just to see how we can develop our retrievals. Our idea is that if we fly the mission, that we do the same thing, but then we compare to the PDFs of the real world, and just can then validate these class resolving models with real data. So what we want to do with Harmony is to resolve stress in the Earth system. So Harmony is not only about the ocean, but also about the solid Earth and about ice. I'm not going to talk about that. I'm mainly going to talk about the ocean in this talk. But of course, I'm happy to tell you more about the other parts as well afterwards if you're interested, and you can contact me about that. So the Harmony science, so we have Harmony science objectives on ocean-atmosphere interactions and the surface dynamics. We want to characterize the air-sea interface, the lower troposphere, and the upper ocean at the kilometer scale. So we want to quantify and disentangle the adjustments between ocean features and the marine atmospheric boundary layer and associated tropospheric clouds under different environmental conditions. Improve the prediction, evolution of tropical and intense extratropical cyclones, evaluating the feedbacks between these extreme weather events and the upper ocean state. And the third objective that we defined is resolving the high latitude small mesoscale ocean surface dynamics and quantify the submesoscale surface current gradients over all latitudes and seasons down to the order 1 to 5 kilometer horizontal resolution. We want to understand processes, to validate models, and to consolidate empirical parameterizations, targeting momentum and heat exchanges, water cycle and carbon fluxes, leading to precise data-driven representations of these processes in new generation Earth system models. So on the first objective, surface and lower troposphere, here's some Earth system science data showing you the carbon flux, different parts of the Earth system, the energy change in the middle, also different parts of the Earth system where you see the ocean as a major part. And on the right-hand side, you see equilibrium climate sensitivity for CMIP5 and CMIP6, and where you see that by increasing the resolution of these models, also the spread in the results is increasing. So we somehow seem to introduce uncertainty by better resolving these systems. So the real question, of course, is can we reduce the uncertainty in these predictions by better observing what's going on the smaller scales? So this graph is again the same as I showed before. We used it also in the user consultation meeting for the Harmony mission that is leading up to the selection, probably end of September, by the ESA program board. Again, it has all these detailed processes that we, of course, will not be able to explain to the program board, but we hope that they understand that we're looking at the quite complex processes on kilometer scales that we would like to better resolve. Marine atmospheric boundary layer will be measured in different respects. So you see on the left-hand side, maybe it's quite small, but you see actually 3 satellites. The middle satellite is the Copernicus Sentinel-1. It's a synthetic aperture radar, and the synthetic aperture radar is already working. We had Sentinel A, B, and soon we have C. B have actually stopped working. But we also have C and D, so there will be more missions of Sentinel-1. And we plan to fly along with Sentinel-1, have a satellite leading in front of the Sentinel-1 and one at its tail. And these 2 satellites, they will also measure the radar signal that the Sentinel is emitting to the surface. They will measure it from 2 different angles. So we get actually radar backscatter or radar backscatter from the Sentinel-1, of course, and bistatic scattering from the 2 other satellites. That will give us multi-angular azimuthal views of the ocean surface, of the roughness, and that will make it possible to measure wind factor on very small scales, or stress factor if you want. So we get directional roughness. We also put a multi-frequency and multi-perspective imager in the infrared. in both these two additional satellites. So we will able to see the sea surface temperature gradients. Also, when it's cloudy, we will have multiple views for multiple perspectives, and therefore we increase the coverage of the ocean area we can see. So sea surface temperature will be measured, and particularly we're interested in the gradients. As you know, the gradients, of course, have strong association with the changes in the directional roughness. But if we have these infrared multi-perspective images, we can also look at cloud top height and even at the cloud top motion. So these multi-perspective views will have simultaneous views of clouds, but also a non-simultaneous views of clouds and at different angles. And that will allow us to disentangle the, let's say, 3D geometry of the clouds and the motion of the clouds. So using these cloud resolving models, we have simulated how much the clouds change over the, let's say, 5-minute time window that we fly over the scenes, and we verify that we indeed can get motion information from the clouds too. So therefore get some information on cloud processes and cloud entrainment processes. So on the there's some plots that you can see here on marine atmospheric boundary layer roles at the top, and at the bottom you see the on the left you see the surface roughness, on the right you see clouds for some typical conditions. And we would like to measure them in association so that we get some idea of the organization of the marine atmospheric boundary layer. Yes, this is a graph showing both in gray the surface roughness imaged by SeaStar, and in color the SST signature of the same scene. And if you see them flip, you can see the very strong association between both, as you all well know, I think. So that's why we also would like to measure this in association. So Harmony will directly observe the sea surface thermal structure to obtain the 2D co-spectra of SST and of surface stress. SST affects the sea surface winds, and we will observe this down to the ocean mesoscale. So interactions at these smaller scales are only studied through numerical studies, and now we will measure this in the Harmony mission. So what is unique? It's simultaneous measurement of the SST and surface stress on the kilometer scale. And fundamental is that air-sea fluxes depend on the nonlinearity of SST and stress. So the joint variability is quite relevant. As I said already, we also would like to link, and we're going to link the surface conditions to clouds. Clouds over near surface air temperature in cloud resolving model SAM, as you can see in this gray view, where you can see clouds, you can see the sea surface temperature change. Sorry, it's not sea surface, it's boundary layers. I think it's 2 meter temperature that you see here. So you see the downburst, you see the change in temperature due to the downburst, and you see the warmer areas in other places. And so you see the association between the clouds and the surface in this plot. So we will observe cloud top motion and position, providing information on entrainment together with the surface conditions. And we want to identify the processes that lead to different cloud types and the different environmental conditions. On the right-hand side, you see some of those different cloud types that are documented in literature and here observed by the MODIS system. And of course, these different cloud types, they correspond to different dynamical conditions in the boundary layer and to different fluxes. And therefore, it is good to dynamically understand these different cloud types in terms of these fluxes. So going to extremes, For extremes, we have some star measurements in hurricanes, but also here, of course, we are much interested in the directional properties that we will measure in the Harmony mission. So also to get the stress direction right, to get the ocean motion vector from our measurements, and link that to the evolution of the hurricane. Particularly the inner structure is of course difficult to observe with current majority of surface winds that we have from spectrometers. They cannot really resolve this because the structure is very sharp, and therefore also the dynamics is quite difficult to see from these more coarse resolution systems. And Harmony will be able to have that directional high resolution surface stress on those fine scales. In the sea band, so also we have less trouble with rain, obviously. So fundamental is that we will quantify the energy injection into the tropical cyclone Carnot cycle and get a better understanding of rapid intensification events. Of course, there's also the strong interaction with the ocean. So we have this infrared instrument that will, of course, not be able to get the SST structure when it's cloudy, but as soon as it's not cloudy, we will be able to measure the fine scale structures of the trail of the hurricane and be able to investigate the evolution of that trail in time, which also is, of course, important to understand in terms of ocean processes. Then small-scale upper ocean dynamics, resolving the high-resolution, high-latitude, small mesoscale ocean surface dynamics, and quantify the submesoscale surface current gradients of all latitudes and seasons down to the kilometer-scale horizontal resolution. So ocean small-scale process can lead to surprises such as high-impact, low-likelihood events, and we're quite interested to see those. On the right-hand side, you see a plot where you see Antarctic sea ice volume evolving over the years, and you see that the slope at the end is quite different. Actually, the higher resolution model is closer to 0. It does not imply that we think that it should be closer to 0. It's just implying that if you change the model to higher resolution, that you get changes that are quite difficult to understand, and that implies that we really have a lot of uncertainty about those changes over time. So also there we would like to get more better information on the processes to better understand how these things should change, whether the parameterizations that are currently used are correct or not. So we are working on process understanding to improve our system models. As I said, we go to the small scale, kilometer scales, and we want to verify models at those kilometer scales so that we are better able to use those models to also inform the global problems of climate change. So that's essentially how we are planning to work. So I already said we will measure SST with multi-angle infrared instruments, directional roughness, directional Doppler too. So we're able to get the ocean motion from this. We also will measure clouds. So we also get the association between the surface and the top of the boundary layer. Harmony will not be a global mission in the sense of that the spectrometer is. You see in the bottom right plot the typical coverage of Sentinel. That will also be the typical coverage of Harmony because we use the Sentinel mission as a host. And we will fly along only one Sentinel satellite, of course, even there may be 2 in orbit. We can only, of course, group up with one of these. And that will typically give the coverage that you see at the bottom. So we will be able to look at some dynamically interesting regions. We will be able to look at most coastal regions. And we will pair up those measurement acquisitions with model runs. We will compare the observations that we do with the model runs that we do to verify that the data that the model is producing are realistic. And we believe that if we do this over many scenes, over a long period, that we will be able to guide these cloud resolving models and large eddy simulation models to provide better guidance to the larger scale models. Yes, the surface current part is of course very important in the mission too. So we will have current, roughness, and SSTs, and we think that can help us to get better satellite observations of submesoscale flow diversions relative for the strain rate. So the directional qualities for both the roughness and the Doppler are quite important in this respect. So key messages: Harmony will deliver unique capabilities to observe the upper ocean and lower troposphere dynamics. These simultaneous observations will shed light on kilometer scale processes and steer more accurate parameterizations of unresolved scales and fundamental processes in numerical models. Data utilization and mission impact assessment will continue. And of course, we're open to new ideas and previously unforeseen applications to better exploit the total mission, of course. So this was essentially Harmony in a short summary. You see that here on the left-hand side. At the bottom, you see SeaStar. So SeaStar will be a satellite of its own. It will also have 3 views under 3 different angles. It will not be in C-band, but it may actually be in Ka band. It will have 3 squinted beams and 2 interferometric antenna. It will have more coverage, so it will actually cover all coasts, shelf areas, and marginal ice zones. So you could imagine that if Harmony will first be run, it will be a very excellent predecessor of the SeaStar mission, preparing the user community for more data to be obtained with the SeaStar mission in the Earth Explorer 11 competition. There's still 4 left, so the chances of it to be flying somewhere around 2032 is still not sure, of course. Of course, these missions will profit from the heritage, scientific readiness levels that we have for spectrometer data. So we're actually still developing cone metrics for relative calibration and GMF development for spectrometers, and we will plan to use that also for Harmony and SeaStar. We have general tools that we use for our wind processors, which can also be exploited for Harmony and SeaStar. We plan to produce a 20-kilometer product or maybe a 15-kilometer product. It will depend a bit on the evolution of spectrometry. For reference, so of course we anticipate that the coarse resolution products for Harmony and SeaStar actually can be verified with spectrometer data, such that they provide the same surface truth. So we can do intercalibration. We can use the same processor for 1-kilometer winds and evaluate the residuals of the 1-kilometer products with respect to the spectrometers to identify the subscale processes. We'll relate to Doppler, SST gradients, and tip cloud height and motion. And there will still be studies actually on SCA Doppler. So there's a study of ESA and EUMETSAT in 2023 on the Doppler capabilities of SCA, which also, of course, would be nice to prepare for Harmony and SeaStar. Well, it says here SCA will be launched in 2025. That's actually not very accurate. So the plan was to launch SCA at the end of 2024, but actually it may now move as the first EPS second generation satellite to be launched, which would imply that it would actually be launched early 24. And so then actually we would already get data in 24 rather than in 25. With SCA, we also, of course, getting more data closer to the coast. We're working now on coastal processors. We have a lot of heritage on the accuracy assessment and calibration of these instruments, and that will be used also for Harmony and SeaStar. And that's the end of my presentation. Thank you.
Thank you very much. This was wonderful. Questions for Ed? And while people are thinking, I'll ask some questions. First of all, just some practical things. You did a great job going over the science, but I wondered about some of the more mechanical details, like how big is a scene and what's the revisit time? And what launch date are we talking about for Harmony?
Yes, yeah. So in terms of the scene and the revisit time, we actually can only do what Sentinel-1 is doing. So it's exactly the same.
And what is that, just for reference?
Oh, yes. I showed you a map on the slide with some patchy acquisitions.
Yeah.
Those acquisitions, so the scenes are the mode that is most used has a 500 kilometer swath width. It's employed very often in the Arctic. It's employed for campaigns on tropical cyclones, or I should say it was, because that is a special program that is on and off. And it is employed in over the ocean in physically interesting regions, western boundary currents, not all of them, but some parts of it, ITCZ parts of it. So in the mission development, we have quite strong restrictions on duty cycle. So we cannot put the Sentinel-1 mission on all the time, that's for sure. But there is like a 20% flexibility on where you make acquisitions. So we have some opportunity to look in dedicated scenes that we want to revisit, and the revisit will be, I think it's weekly, always if you want, but it can be faster for certain areas because it depends on the also on the ascending descending configuration.
So that's really different from a polar orbiter that is trying to sample all the time. Really complementary, I think.
Yes.
And you may have said this, but what's the launch date anticipated for Harmony?
So Harmony is now planned for 2030. And given the, let's say, the technological readiness that we went through, of course, when preparing the mission, we think that is quite feasible. The main questions are now on the infrared instruments to keep them within the cost budget. So at first they were going to do SST and motion and roughness. You may know that I've been proposing this tandem clouds infrared mission in the past. And at some point they decided they might as well do that. So that I was put back in. And yes, I'll be running these cloud resolving models again to see how we can do that. And it appears, well, we want to have 5 views for each infrared instrument at 5 different angles. And there should be then 3 should be simultaneous. So and 2 will be sticking out of each instrument. So we would have a large enough time base to get motion information, and also have simultaneous data. So we are not we will have less issues with aliasing of motion and position, because that is one of the issues with the Maestro mission, which is doing everything from one platform. So that's the idea, and there's now still some technological studies going on in 3 different teams to look at the feasibility aspects of this.
Thanks.
I have a question.
Go ahead, Ralph.
You're talking mostly about comparing the harmony measuring simultaneously with the standard sort of Sentinel-1 imaging modes. Will it run, can harmony run relatively continuously and also make its measurements against the wave mode data that's collected more frequently?
Yes.
In the ocean?
Yes, you're right. So the way I did not show the wave mode on the map, but the wave mode is a small 200-kilometer imagejet it's every 200 kilometers, I think. So that will also be measured by the 2 other satellites. So we will have small patches globally, but in terms, let's say, of global coverage, they do not contribute a lot to getting really global data, I would say. But yes,
they contribute quite well to the sampling of conditions, though. I mean, you don't get a lot of cover a lot of conditions globally. So yeah, that'll be interesting.
Yes. So indeed, that mode is on, and also we have discussions about having the tier on, of course, the infrared instrument, because it does not depend on the Sentinel-1 in principle.
Certainly the infrared would be really good to have against.
Yes. Yeah. So that's also still under discussion, but not yet decided. But of course, we would like to extend that mission beyond the Sentinel-1 acquisitions.
Great. I see that Tony Lee has his hand up.
Thanks.
Hi, Tony.
Hi, Art. Thanks for the nice and comprehensive overview of harmony and SeaStar. You may have mentioned it that I have missed about the expected uncertainty of the surface current measurements.
No, I did not actually show uncertainty measures. So we target 1 kilometer scale, and from the top of my head, I think it's 0.2 meter per second random accuracy.
Okay.
So our idea is that we actually can also play with resolution and then get better accuracy on larger scales. But we'll also be able to resolve, let's say, fine scale, strong shear environment conditions with the 0.1 on the kilometer scale.
Right. And I noticed that you have been emphasizing the current gradient, and that's important. But is it that it has better ability to measure the gradient than the total current itself? Or is it
no, actually, I was actually stressing the gradient capability of the SST.
Okay.
So the Doppler measurement, of course, we have a similar problem for the Doppler, because the absolute calibration of the Doppler is also not easy. But for the infrared, we required actually that we are able to measure the gradients very well, better, so not the absolute temperature. Our idea is that there will be SST missions around that can give us the more global temperature information at every location. and that if we get the local gradient information, that we can use that to investigate the small-scale processes.
Mm-hmm. So total surface current is one of the mission requirement.
Yeah,
not
yeah.
just the gradient of the current. Correct?
Yes, yes, yes,
Okay.
that's correct.
Okay.
Yes. Yeah.
Mhm.
All right. Thank you.
Other questions? People can put questions in the chat or raise your hand under the reactions button. But I also wondered about data volume and access to data.
Yes, it's of course still far away, but of course we thought about that. One of the issues with the infrared instrument operating continuously is actually data volume. So you might imagine that. So we have to, if we want this, we will have to look for solutions to that. And that will be one of the, let's say, further design issues that we will face in the coming few years.
And are the data intended to be open access?
Yes, the data is intended to be open access.
Wonderful.
Yeah.
Yeah, it'll be exciting.
Yeah.
Ernesto, do you want to go ahead?
Yeah, hi, Ed.
Yes,
So one of the things that the C-band papers looking at currents have shown is that you have to be very careful removing the wind signature through geophysical GMF. Is there going to be pre-launch campaigns designed to try to get a look at the current geophysical GMF better? And if so, are they open to other participation?
The last question I'm not sure about, actually. The first part of your question, yes. So there has been already a Waddenzee campaign in the Netherlands. So if you're familiar in our environment, you may know we have these sand islands in the north, and we have tides. So we quite precisely know the tidal currents in those areas. And so we did some campaigns to fly over those areas to see whether the tides or the ocean motion that we see from the airplane measurements can be linked to the motion that we know from the surface. And we plan more campaigns also for the tier. So yes, we are planning campaigns, and I think we did also need to discuss participation if you're interested, because from a scientific point of view, this of course would be quite fantastic. So I would certainly vote for it.
Well, the ability to measure currents from space is still open, I think.
Yes.
All these campaigns really help every Doppler measurement from space. So
Yeah.
Have the results been published? I may have missed them.
No, there's no published results from these campaigns. They've been quite recent. So actually still working on them. There's also been a SeaStar campaign that was actually running while we were at the Living Planet Symposium this spring. And also those results are not yet published. Actually, that campaign was partly successful, I would say. But I've not seen the results yet, so I think that will also take some time to digest the data and publish.
Okay, thanks.
Any other questions? I wanted to ask one more thing, and this is just betrays my inexperience and naivete, but you're talking about measuring infrared SST, but we also sometimes are able to get microwave SST from scatterometers. Is there any microwave capability intrinsic in SAR or in this planned instrument?
No, in the C-band we are not able to get SST information.
So microwave SST would come from it.
Sorry.
Microwave would come from other missions flying at the same time, as you said before.
Yes, so the larger scale SST.
Yeah.
Will indeed be taken from other missions. Yes.
Are there any other questions? Well, if not, this has been really great. Thank you very much for sharing this with us. I think it gives lots of food for thought about future science and future synergies with other things that may or may not be funded.
Yeah, my pleasure, really. Yeah. Looking forward to collaboration on this topic. It's really exciting, I think.
Yeah. So, well, a big round of applause and thanks a lot.
Okay, thank you.
Thank you very much, Art.
My pleasure.
Bye-bye.